All right, the next section, 14.5, is really where a lot of important things come out. And this is certainly a section that is well worth your time in reviewing and making sure you understand everything from this. So, 14.5, we introduce the idea of the gradient. So, the gradient is specifically this context. When this symbol, which we can just say nabla, sometimes people call it del, when this acts on a scalar function, so this f is a scalar function. Why? Because there's no arrow over it. This is just f. So, when you act on f like this, you can literally think of it as multiplication by this vector. So you can think of it as del del x, del del y, del del z, multiplied on the left by f. This gives us del del x of f. Well, that's del f del x, which is no different than the x partial derivative. So these become x partial, y partial, z partial, which is exactly what we have right here. It's important to emphasize that this alone is not the gradient. This, when it acts on a scalar function, is the gradient. So the gradient is a way of collecting and consolidating all of the individual ways this function f can change. Chain rule for paths. So, if you have a function of some number of variables, let's say 3, and in the domain, so here let's point out that the domain of f is, let's call it D, is a subset of 3 dimensions. So this means whatever the domain of this function is, it is 3-dimensional. The domain is 3-dimensional. So if the domain is 3-dimensional, more or less, or at least we have that possibility, in general it's 3-dimensional, then we can think of a path in the domain. Path in the domain. So that's what R is. R is a path in the domain. To the domain space of the function f. So in other words, if we only want to look at the value of this function f, we're only interested in the value of f on the x, y, and z points that make up this path in 3 dimensions, then we can calculate the rate of change of the function f with respect to the parameter value, or time, if you want to think of it as time. And this is the same chain rule, more or less, as what you learned in Calc 1. You take the derivative of the outside function, you leave the inside alone, multiply by the derivative of the inside. But there's some small changes. Since the outside function is a function of 3 variables, when you take the derivative of that function, it's not just f prime, rather it's the gradient of f. So here, the gradient of f is the derivative of the outside. We're going to leave the inside alone, that's self-explanatory, and then we're going to multiply by the derivative of the inside. But the inside is a path. It's a vector-valued function. So this is a vector with 3 components. So when we take the derivative of it, it's still a vector quantity. So how do we combine a vector quantity with another vector quantity? Well, there's 2 types of products. There's a dot product, and then there is a cross product. Right? There's a cross product. So it just so happens that the proper way to do this is a dot product. So to contrast the chain rule for paths, we can take a look at the directional derivative. So this is also has to do with a function f. Let's say f is a function of three variables, x, y, and z. So then the domain of f is three-dimensional. So in our domain for f, so let's say here's our three-dimensional. Let's say here's some point p in the domain of f, and then let's say there's a point. Let's zoom in really close. Let's say there's a point really close by here. So if we want to know the rate of change of f if we were to move this very small distance from one point to another, we would really just want to know what's the rate of change of f in this direction. So what we can do is specify a direction with a unit vector. So what we could do is find this vector and then just make it have length 1. And then what I like about this expression here is that the gradient of f I already mentioned is a way of consolidating and collecting all of the different individual ways that f can change. It sort of quantifies all of the ways in which f can change. And then what we do here is once we know the direction that we want to move in, then we can just extract how the information that we're interested in. Literally, I view this dot product as a way of extracting from f the rate of change of f in this direction u. So we're really just asking the gradient of f, hey, what's the rate of change in this direction u? So I always think of the dot product as like an extraction method. So this notation here stands for the directional derivative of f in the direction of u, and this u is assumed to be a unit vector. If this vector u is not a unit vector, then it imparts an additional amount of, it alters the rate of change in an inaccurate way. So the main difference between these two things is here, what this is actually capturing, this is capturing the natural rate of change due to the nature of the function alone and nothing else, where this actually takes into account the path you're on. So if this function represents maybe temperature in a room, and this r of t is the path a person takes walking through the room, then obviously if they are running through the room, so maybe your velocity here is very big, it's a long vector, then it will certainly mean that the person will experience a faster rate of change of temperature. Because if you're running, you're going to experience a rate of change faster than if you were walking and your speed were small. So this is sort of assuming you're walking at speed 1. So in a sense, it's only examining the geometric rate of change due to the geometry of the function. Where this is saying, okay, we're going to take that geometric rate of change into account, but not only that, but also how fast you're moving. So one way we can visualize this essentially is imagine you're on a hill, right? So at this point right here, so let's kind of make this three-dimensional right here. Okay. So if we're at this point, and let's say we're going to move in, so the steepest rate of change, so like downward might be that, and the steepest way to increase your rate of change might be that way. But let's say we're going to move in this direction here. If we move in this direction, what's the rate of change? This, so if we say this is our unit vector u right here, this will report back like what the curvature, not what the curvature is, but it has to do with the slope and the curvature of the actual topography of the landscape, the actual hillside. Is it very steep? Is it not very steep? It only takes into account the actual like topography, the geometry of what we have. Where this will be like, okay, I'm going to move in this direction, but I'm going to run really fast downhill. Okay, so that's going to be different than this, if that makes sense. Okay, a couple other things here that are really important. Some interpretations of the gradient. The gradient always points in the direction of the maximum rate of increase. So for instance, if I were sitting at this point here on the hillside, if I wanted to, and let's say that this right here is the graph of z equals a function of x and y, then if we now think of a bird's eye view, let's say that so this is the z-axis, let's say. Okay, so here's the x-axis, here's the y-axis. So if we do a bird's eye view, oops. So there's the x and y axes. So if this point, if we think about dropping it down onto the xy plane, maybe it's on the x-axis, so maybe it's like 2, 0. So then we're like right here. Well, where would we want to go to increase our altitude the most rapidly? We'd want to go uphill. We'd want to go towards the z-axis. Well, the z-axis is coming out of the page right here, so the gradient, so this is the point P, so the gradient of f at the point P would be pointing in this direction. It would tell you to go that way. It always tells you the direction that you should move in your domain space to increase the value of the function the most rapidly. On this diagram, we'd have to go up the hill, which means since the peak is at the z-axis, it would say to go in the z-axis. In this picture here, the perspective drawing in 2D, a 3D thing is a little bit, it can cause some issues here. All right. Negative gradient, so if you want to calculate, so this right here, the negative gradient always points in the direction of the maximum rate of decrease. So if you want to decrease your altitude as quickly as possible, you would probably move in this direction, which is exactly opposite of the gradient. So the gradient is always to increase most rapidly. Negative, the gradient is to decrease the most rapidly. Lastly, the implicit form down here of the equation of the tangent plane is possible by the fact that if you have something in this format, so for instance, I could take the equation of the unit sphere. Or unit sphere. Right, if I really wanted to, I could take this 1 and move it over here, right? You don't have to. Some textbooks have this just as k, some constant. As long as all of your variables are on the one side, which ours are, then this will work. So what I can do here is I can call this left-hand side, let's just define that to be capital F of x, y, and z. Then the equation of the sphere is given by This equals 1. So if you take the gradient of this function that we just defined, we'll have 2x, 2y, 2z, and this right here serves as a normal vector to the surface of the sphere. We call this the implicit form because this is an implicit surface. It's not solved for one of the variables. Where the equation of the tangent plane we did earlier, right here, this is made possible by the fact that you're starting with something in the format z equals a function of x and y. It's already solved for one of the variables. Here, we're not making that assumption. So this is very nice to use.